I'm glad you're coming back. It's a great pleasure to speak at your conference for COVID. I've known you both for almost 30 years. I mean, I remember when I came to Jerusalem as also in 1994, and Kobe came to a seminar from Philip. He was one of the familiar faces, so I don't remember when exactly we first met, but for a very long time. So it was always a pleasure to interact with you. And actually, at the Fields Institute at some point, we found out that Kobe and I should have formed the same hospital in Jerusalem. But that was very bizarre how we found it. So anyway, the topic that I want to talk about has its origin not really from a model theoretic question, and lately it's become fashionable for non-model theorists to talk about first order rigidity. So I feel it's not really a model theoretic question, but well, it has some model theoretic content, of course, and also it connects in this case, because the model theoretic content is the title of my talk. It really connects to your work of Kobe and Sergey on the bi-interpretability of the simple algebraic groups and their underlying fields. So in joint work with Dan Segal, we extended this, and if it's not a very exciting model theoretic piece of work, I think it, or at least I hope that it will be very useful because it applies in the one context. So thank you. I should have tried this. Where do you...
Right now?
Is it on? Where do you press the mute?
The slide.
No. Okay, the motivating question is the following. If you take a class of groups, you can ask for which groups in this class is there a single first order sentence that will describe the group up to isomorphism within this class. And here, a first order sentence we think, of course, of in the language of groups. So we want a sentence such that if G and H satisfy this sentence, then H and G are isomorphic. And of course, if such a sentence phi exists, then we call the group G finitely axiomatizable in this class C. And Vygotsky and his collaborators, they call the group first order rigid if any finitely generated group H elementarily equivalent to G is isomorphic. So first order rigidity specifically talks about the class of finitely generated groups, and it is not asking for a single sentence, but for the full first order theory. So it's related and closely related, but as model theorists, we know the difference between these two concepts. So of course, if we take the class of all groups, then the group can be finitely axiomatizable in this class only, or if and only if the group is finite. And one direction is Löwenheim-Stollen, so I don't want to stand and point it in computer. So, of course, one direction is Löwenheim-Stollen, and the other direction is obvious. If you have a finite group, you just write down the multiplication. So here, in some older work with Ambellis, we asked how long a sentence do you need to describe this group G. So, and here, of course, in the infinite setting, it's kind of similar. Is a single sentence enough to describe the group up to isomorphism in this class? And there we were asking how long a sentence do you need? So how much information can you compress into a sentence of a given length? And what we showed was that for any finite group, there is a sentence of length in the order of log G cubed that describes G up to isomorphism. And if the group is simple, you can do much better because it's actually enough to have a sentence in the length of log of the order G. And a lot of this work in the simple case in particular really can be done very easily, quoting heavy results by Alex and his collaborators, because they found very short presentations for these finite groups. But there were some exceptional cases for which no short presentations were known, and so in the simple case, this is really kind of new description in this way, and it used also the bi-interpretability of the field and the group. And in fact, it's one can see that this bound is optimal just by the sheer number of p groups, because there are so many groups of order p to the something. This number grows. This length has to be at least that, otherwise there are not enough sentences to distinguish all these groups. So from that point of view, this is the best possible bound. So now for infinite groups, you can again ask how much information you need to pin down the group up to isomorphism. And of course, if the group is finitely axiomatizable within this class, then it's again just a finite amount of information that determines this group within the class. And to give you a famous non-example, if you take the class of non-abelian free groups, then of course by Segal's results, we know that all non-abelian free groups are elementarily equivalent, so there's no hope to distinguish one from the other. On the other, or here's another example, if you take the class of groups, just to be silly, I put SF5K for K in algebraic closed field of characteristic 7, then all groups in this class are elementarily equivalent, because all the algebraically closed fields of characteristic 7 are elementarily equivalent, and we'll see in a moment that this is enough to conclude that the class cannot is just, of course, one class in a more theoretic sense. Also, there could be silly reasons why a group is finitely axiomatizable in a class. For example, if you take a class of groups, for each prime you take a single p group, and let C consist only of these groups, then of course you can distinguish every group in this class by a single sentence. But of course we're not interested in this setting. Conversely, there can be inherent reasons why a group cannot be FA in a reasonable class C. Namely, there's this old result by Agnes Schmierlev, and which was extended by Roger and Sabat. If you have a group such that the center modulo the derived group is not a torsion group, then actually for any first order sentence, if it holds in G, then it also holds in G direct product with the cyclic group of order P. So in particular, from that you see that if you take the integers, they certainly have this property that the quotient is not torsion. Any sentence phi that you can find will also hold in Z times and direct product cyclic group, so no chance to define class, or the same for the profinite completion. So when we talk about this, of course, we're looking for reasonable classes, so natural classes for which we may actually be interested in knowing that the group is FA in this class. So it's kind of meaningful. And the classes that I'll focus on in my talk are finitely generated groups, profinite groups, and locally compact groups. And in fact, more precisely, we'll show that for simple Chevalley groups of rank at least 2 and appropriate rings, but this is the restriction on the rings are very small. They are finitely axiomatizable in the corresponding class, and class corresponds to the kind of ring. So if you have a finitely generated ring, then we talk about finitely generated groups, etc. I'll say more in a moment. So to show that for appropriate rings and simple Chevalley groups of rank at least 2, the groups are G of R are finitely axiomatizable in class C. We show that R and G of R are bi-interpretable, and this is was the Segal's result of the model. And then use that the ring is finitely axiomatizable in the corresponding classic rings. And for rings, there are a lot of known examples. Every finitely generated commutative ring is FA in the class of finitely generated rings. So this is very recent by Matthias Aschenbrenner, and Z is Segal, I forgot who the other. Yes, K is Philippe, yes, and then I don't remember. NST is underneath Dan Segal and myself, and Aschenbrenner and Stefan are recognizable. So here we have a list of examples where we have natural rings in natural classes, where we have finite maximizability. So finitely generated commutative rings were, well, here regular unramified complete local rings that are long named, but what you can imagine are just power series rings of this form in the class of profinite rings. Local fields are A in the class of locally compact rings. And here's a counterexample. This counterexample is also due to Toscana. If you take a direct product over infinitely many primes of the p-adic integers, infinitely many p, then it's not finitely FA in the class of profinite rings. So, and of course, we all understand why this is not surprising. This last. Okay, so for rings, we have a number of examples. Now, I want to talk a bit about bi-interpretability, because maybe it's not a concept that everyone is aware of. And it first came to my attention when you proved it for algebraic groups and the underlying fields in the all-minimal context. So suppose we have two structures in two different languages, a priori completely unrelated. So of course what we have in mind here is one is a group, so in the group language, the other one could be a ring in a ring language. And then we say that the structure M1 is interpretable in M2 if there is an L2 definable subset of some power of M2, which plays the role of the original M1. And for each L1 definable subset of the original structure, we find an L2 definable subset of the copy that we found inside M2 to the N. And because we have to take k copies of M1 tilde, we need n times k copies of M2. And furthermore, we want an isomorphism between the original structure M1 and its copy inside M2 to the N. And here we're not talking about definability of the automorphism, because it would even make sense. It's from one structure to the other, which is not an abstract isomorphism. So this is the notion of being interpretable. I'm sure most people.
But shouldn't we also take the quotient of M2 to there?
Yes, we should actually allow quotients. Yes. Actually, here we don't need to take quotients. That's why I gave this name.
But here you mean where?
In for what we're doing, we actually get by integer. So yes, but that's right. And bi-interpretability means one is interpretable in the other and in both directions. And the composition of these two abstract isomorphisms is actually definable in, so this composition is L1 definable from the original M1 to the copy of M1 inside the copy of M2 that we found inside M1. So if you have a field and you define the algebraic group as a matrix group inside of k to the n squared, And inside this, you find again the underlying field. Then you want an define the isomorphism from this field that you originally started with to the copy of the field inside the matrix group that you defined, and in both directions. And the point of bi-interpretability is that somehow we feel that they have the same complexity of definable sets once they are bi-interpretable. So what we showed in our joint work with Dan Segal is that if you take a simple adjoint Chevalley group scheme of rank at least 2 and some integral domain, and in most cases we don't even need that R has any units other than the identity, only for groups of type En, and therefore do we need that R has at least 2 units. Then R and G of R are bi-interpretable. And there were predecessors to this kind of result. I think the first one was Voisin in his note on Chevalley, where he showed this for algebraic closed field. Then for real closed fields, Kobe and Segal showed it, and for pseudo-finite fields with automorphism, Wrighton showed it. And
when you do like to quote it in parameters.
yes, with parameters. Yes, absolutely. Yes, I say what parameters. So it would be very nice to have this for rank 1 as well. That is very far out of reach in this generality for all things. So this, I'm not true. What? No, it's not true. Yes, it's not true. True, but even yes.
Sure.
Yeah, no. Even to say exactly for which range we may have it, it's out of yes. Yeah, also it's out of reach because it's not true. There is, in a more general setting, if you take any, so this is a result that starts with rank 1, because K isentropic just means that you have some torus defined over this field K, so the group can have rank 1. But here we're assuming that K is a field, and then you can show that the field is definable in this algebraic group. And for that, it's the standard way that was used by Lower and Titz also, that you use the action of the torus on the root subgroups. And since the torus, when it acts on the root subgroup, first of all, acts by multiplication of squares, this kind of argument works whenever every ring element is of the form x squared. So if every element is a square or the difference of 2 squares. Even in rank 1, for example, for some complete local rings, one can use this to define the field or the ring and get bi-interpretability. But unfortunately, there is a result by Yarden and Haran, I think, where they show that for many rings of algebraic integers of number fields, you never have a bound on the number of squares that you need to present from units. So even in a priori cases where one could hope that it holds, there's no obvious way to do it. So obviously this torus action cannot work if your ring doesn't have any units like the integers, for example. And the key step, which I just said casually, well, of course, the root subgroup is the double centralizer of itself, of an element in it. And then everyone will ask, yes, of course. But it's really, there's no statement that actually proves it for rings in particular, because the people working in algebraic groups, they think this question is not even well posed, so one shouldn't even ask this question. But it turns out to be really a nice, I think in itself, it's a very nice result. If you take a simple Chevalley group, and in these cases, type B60, 78, or A4, we need more than one unit. And also type CM, we need more than one unit, but that can be changed. So then if you take any root subgroup in this group and let Z denote the center of the group, then the double centralizer of this element U is exactly the root subgroup extended by the center. So then by more precisely, we can find a finite set of witnesses Y in the centralizer here, such that the centralizer of these elements is contained in the root subgroup times Z. And this even not specific for any ring, but just in general. And the same statement holds for any simple R isotropic group. So if you have some torus defined over. And yes, how can you find this set Y? Well, if the ring has enough units, so enough really is not very many, we only need 4 units, then actually we have a very nice uniform group where you just pick a torus witness. So you take some element that acts on this root subgroup and that acts torus fixes 2 points on the projective line and that's regularly on the rest. And you find torus witnesses that act trivially on one root group and regularly on the other. And that, of course, if you want to centralize it, that kills the root group on which you act. So in this way, you can kill all other root groups in the centralizer, and this gives a very nice uniform proof for all times. And to get rid of this assumption that we have at least 4 units, for the classical groups, one can actually do it by matrix computation. You just write down things and check what's correlated with it. It doesn't look nice, but then did it. So, and for groups of type G2, one can actually use the action of the group on the associated kids building, and then because the witnesses can then be chosen as uniform elements, we don't need to assume any that we don't need to assume that there are any units. So that's the nice thing, that for G2 again we don't need any units. And so we can get rid of the center in this double centralizer by taking the commutation relations. And as a corollary, we see that if G and R are as above, then the root subgroups are actually final. And maybe I should write down an example of what such a root subgroup looks like in case you have not come across something like that. So, can you read here? So, for example, if we take SN3R, so we have these strictly upper triangular matrices, and the root subgroups correspond to the ones that have an entry just in one place. So this is one root subgroup that has entries from the ring there, or guess what the other ones are. You have 3 root subgroups, namely corresponding to the 3 positions, I mean, this to these 3 positions in this upper triangular matrix. And now when you do a commutator, that's what I mean with the commutation relations. I don't know, talk about that in a moment. So when you multiply 2 matrices of the same root subgroup, so So if you take something 1, 1a and multiply it at 0, 0 here, 0, 0, 0 here, and multiply it by this, then you see that you just get the addition that you see. So this root subgroup is really isomorphic to the additive group of the ring, which is very nice. And also for all root subgroups, we have definable maps. Namely, we have elements in the group that take one root subgroup to the other root subgroup. Just conjugate. And now that we have identified the root subgroups and the kind of gauge the root subgroups in a uniform way, then you can see that if you take the commutator of, let me make it explicit again. So if we, this is perfect. If we take the commutator of an element of this form, with an element of this form, and the commutator actually gives us the multiplication in this place. And since we can identify the root subgroups in a nice way, using these conjugating elements, once we have the root subgroup, we can actually define the multiplication from these commutation relations that you can actually work out by hand in this case. And these commutation relations are well known and described for all algebraic groups. So whenever you have an A2 diagram, you can actually define the multiplication very easily, exactly in this way that I described. And as a corollary, we then see that the ring as a ring is definable in the group G of R. And the other direction is, of course, almost trivial. If you have a matrix group, then you can define an algebraic matrix group. It's definable in this ring structure. And the matrix multiplication is exactly the group multiplication. So now the question is, we need to, for the bi-interpretability, we need to show that composing these interpretations will be defined. And so, of course, once we start with the ring and define the group as a matrix group in R to the n squared, then the next step is we define the root subgroups in G of R. Yes, and on these root subgroups, we define the ring structure from the commutation relations that I just described. And then it's actually well known, we find it in all books on V groups, that this map R to the Rn squared, R goes to this element in the root subgroup, is algebraic and hence definable in the ring structure. So this is kind of old. It's known and very canonical. Yes, so this is exactly the required isomorphism between the original ring and its avatar inside the matrix group in this R to the n squared. For the other direction, we need that the elements of G of R can be defined by a bounded, the product of root elements. I mean, maybe there are other ways, but this was the only way we could think of. When we start with G of R, of course we can define the root elements. We saw that, and we know how to transport the ring to the original ring, but then how to define the isomorphism from the original root to the copy inside here. That's the question. And in order to do that, somehow we needed that the ring has finite elementary width. That is, that the group G of R can be written as a bounded product of root subgroups. And it's just a product.
So this is the definition of this finite element.
Yes. And if you have that, then of course it's canonical again what to do. We start with this group, define inside it the ring on a root subgroup that we know how to define. Then we use the maps to define these conjugation maps from the bi group essentially to define all the root subgroups by conjugating them all in a fixed root system. Now we have this ring U, the U's sitting on the root subgroup, and now we can take a power of n squared power of alpha inside this n squared power of g to the I, and we can define a matrix group there. And now we can define the isomorphism from the group to its copy inside g to the r, g of r to the n squared by taking every element to its natural copy inside here. And if we have finite elementary width to extend the two products in the canonical. So if g of r has finite elementary width, this is a well-defined isomorphism. And in fact, this argument works whenever there is a reasonable finite product decomposition of g of r. So, and we found a very nice result by Stepanov. He, it of course for model theorists, it's just a compactness result, but he's actually proving it without model theory. But the statement says there is some number n, depending only on the root system, such that for every root alpha and every element in this group G of I, this root element that represents 1 in the ring, conjugated by any element here, is a product of n elementary root elements. So that's very nice. And it's exactly a compactness argument. So if G of R is adjoint, so the center is trivial, then we know that in order to consider the centralizer of an element, the conjugates will be a product of n elementary root elements, so we can write them down. And if G of R is adjoint, then the centralizer of this is just 1, the centralizer over all the different root subgroups. And so now again, every G in the group G of R can be definably mapped to the unique element in the matrix group that has the same action on X on this specific root element, because the centralizer is trivial. So then we get again this definable isomorphism from the original group G of R to the copy. And so as a corollary, putting all this together, we see that if G is, as before, not necessarily adjoint, if it's adjoint, we can use that. The group G of R is bi-interpretable with a ring in each of the following cases. So if it's a field, then it's essentially, it comes from the Bruchal decomposition. That we have finite elementary width. If R is a local ring and G is simply connected, so if you take SLN rather than PSLN, and then the finite elementary width is due to AB and Babylon, and if R is a Dedekind ring, so you see there are many kinds of rings for which this finite elementary width holds. So and for adjoint groups, we get it right. So in this bi-interpretation, we have, we see the following. If the group is finitely generated, then G of R is finitely generated as a group, then R is also finitely generated as a ring. If G of R is profinite or locally compact or TDLC, then the ring is also profinite locally compound TDSC, etc. And if it's a field, G of K locally compound, then K must be a locally compound field. So because the bi-interpretation is just deduced from the group operation. So if the group was had any of these properties, then everything was defined in terms of this group. And thus we obtain as a corollary that if G is of adjoint type of rank at least 2, and well, again we have to assume that we have enough units for the E and F and F4. Then, then the ring is finitely axiomatizable. If the ring is finitely axiomatizable among finitely generated rings, and not all finitely generated rings are, cofinite rings locally compound, then the corresponding group G of R is finitely axiomatizable among the corresponding classes. So it's all a very canonical translation. And so this is happy birthdays to, it's too late for you, but it's on time for Isabel. So it's her birthday today. So congratulations to Kobe and Sage, and I hope Kobe gets well soon.